All right, Algebra 2 people, we are on page 273. Hey guys, don't yell, I'm making a video. We're on page number, you guys, I just said please don't yell, okay? I'm making a video. All right, we're on page 273, and we are going to talk about functions. What we've been talking about is radical functions, graphing the square roots, solving for the square root or any kind of, third root, fourth root, fifth root, all of those types of equations. They're extremely important in science. Now we're going to look into is functions and like what can you do with you got one function doing another thing, you got another function doing another thing, but sometimes in reality they're going to mesh with each other, right? They're going to interact with each other. So I think that this example on page 273 is a great example because it gives you an idea that I can actually perform operations on functions. I can add, subtract, and multiply them just like I could polynomials, just like I could numbers. I mean, everything. I can actually multiply and add and subtract, divide functions. Okay, so in this specific example, I'm going to just go ahead and read it. In business, the term profit is used to describe the difference between the money the business earns, that's revenue, and the money the business spends, costs. So you have the money that comes in and you have the money that goes out. So A, Grooming USA charges $25 for every pet that is groomed. So we're going to let X represent the number of pets groomed in a month. So let's define a revenue function for the business. All right, now this takes us back to Algebra 1. You basically have every time a pet comes in, all right, it's going to be multiplied to $25, right? So if I have one pet, it's 25, two pets, it's 50, and so on and so on. So this is a relatively simple function. So for A, what I have is I have a revenue function that I'm going to call capital R, and in the business world, it's always a capital R. I have a variable that we specifically called X, okay? That's the number of pets. Now the revenue generated from the number of pets that I have as my variable is going to be multiplied to the cost of each of those pets that are brought in. So that is a revenue function. Now, mentally, you probably understood that. 3 pets, $75, 4 pets, $100. You knew that. But this is actually a great algebraic representation of that process, okay? So this is the revenue function. This is the money coming in. But that's not the only aspect of a business. You don't just collect money. You have to put money back into the system and so that it actually works. All right, so that you have supplies, cleaning supplies, you got to pay workers, help, etc. Now, materials and labor for each pet groomed costs $15, but the business also has fixed costs of $1,000 each month. That could be in rent, licensing fees, etc., etc. So there's all kinds of things associated. And the bigger the business, the more complex these things are. So we're going to call this the cost function, right? Okay, so the revenue function, money coming in, cost is the money going out, and 15 of that goes into supplies for the pet each time, but then every month, all right, it has to actually add $1,000, right, of cost for whatever reason. We don't know what it is. Now, if we go to the C, letter C, last month Grooming USA groomed 95 pets. Did they earn a profit? So I hope that you can kind of see that mentally what's happening is that if you want profit, what you do is you have a new function. This function, okay, the profit function means that if I took all the money coming in and if I subtracted all of the costs that went out, that's actually my profit. It's the money left over. So what I'm doing here is I have a function here that is its own function. I have a different function that's on its own, and I can actually put them together in one larger function to demonstrate profit. Okay, so revenue minus cost equals profit. Now what I can do is I can actually simplify this algebraically and say that P of X, okay, actually, instead of plugging 95 into each one of these, why don't I well, I'm going to do that anyway, but why don't I actually just figure out what R of X minus C of X actually is? So let's look at this. 25X minus parentheses 15X plus 1,000. All right, now notice I did put that in parentheses because that $1,000 is a cost that needs to be subtracted. So when I simplify this, I will get 25x minus 15x minus 1,000. And you can see that what happens is that these two terms simplify to a 10x, meaning that if I'm getting 25 in and I'm having to put 15 in supplies, I only have a profit of $10 per pet. So that's what that represents, right? And that's what's happening algebraically. Then if I subtract $1,000 as my overhead costs for the whole month, then that's going to be calculating my profit. Okay, so this is my new P of X. I've actually done a function operation here. I've subtracted two functions to make a kind of a larger function, okay, if you want to call it larger. All right, so now if I want to know if there was a profit, I'm going to go ahead and plug in 95. So I want to know what P of 95 is. That's 95 pets. Okay, so 10 times 95 is 950. So if I were to subtract 1,000, it looks like I have negative $50. So that means for the month, an entire month, I've lost $50 over the whole month. So not a profit. Now, is that going to change with 110? So you can see farther along, what would the profit be if the business grew to 110? Well, let's see. I imagine that is going to turn out a profit here. I'm going to plug in this. So that's going to be, yep. Okay, so 1,100 minus 1,000 is going to be 100. So it looks like there's only a profit of $100 in this situation. And that's a difference of 15 animals more, and I've actually made a profit of 100. Okay, so that's the idea of function operations. That's pretty much the whole point. So what we're going to do is I'm going to show you some further examples in the next video of how to do adding, subtracting, multiplying, and we're going to leave the composing of functions for a separate video. All right. Okay, so let's do that. We'll stop right here.